Okay, so in this chapter 14, we talk about the key thing is about the circuit diagram, understanding the circuit diagram, the components, as well as series and parallel circuit. Okay, what are the formulas that you can use to calculate current, potential difference, as well as resistance? So you need to remember that in the series circuit, okay, you remember that this thing, first of all, the battery, the long is positive, short is negative, and the current comes out from the positive. Always remember come out from positive, all right, the longer side. So in the series circuit, the current is the same throughout because there's no branch. So imagine the current is like water flowing in a drain. If there's a single path, the amount of current is same throughout. Now the potential difference is like, the potential difference is a sum. For example, the potential difference of the battery, the EMF of the battery, is equal to the sum of the potential difference in a series circuit. So you can imagine potential difference is like the slope, you know, where the water flow from high, this side is a high, let's say 6.0 volt, and this is 0 volt. So what happens is that the resistance is the same, means it's 6 volt, 3 volt, 0 volt. So it goes down the potential from 6 to 3 and then 3 to 0 if they are the same kind of resistance, same resistor. All right, so potential will be decreasing proportionally across the resistor. So down here, okay, look down here, they say that, oh, anyway, they give you the reading here is, let's say 1 and 2. So let's look at 1 and 2. If I have 1 volt here and 2 volt here, obviously my voltage here must be 3 volt. 3 volt. Why? The high potential, the positive side is 3 volt. The low potential side is 0 volt. So this side, all the wire on this side is all 3 volt. Everything is 3 volt. All right. Up to here is all 3 volt. All the blue color 3 volt. So let me put 3 volt here. Now, if you drop by 1 volt across, in other words, here is 2 volt and here is 0 volt. All right. So you can see 3 drop to 2 is dropped by 1 volt. 2 drop to 1 is dropped by 2 volts. Okay. So this side, of course, is also 3 volt, but this is 0 volt. Can you see the difference? And let me highlight for you the thing, yellow color. Let's say all the yellow color are 0 volt. Anything on this line is all 0 volt, assuming the wire has no resistance. The center will be the 2 volt. So anything here is 2 volt. Okay, so you can see it this way. So this is how the voltage will change. The sum of all the potential difference in the series will be equal to the EMF of the battery. Yeah. Then the resistance is also as easy. Resistance, can you imagine that it's actually the resistance of the flow of the current. So if it's single path, the sum of resistance will be the overall effective resistance. So they put it as a RE, effective resistance. Effective resistance is also the overall resistance. And in this case, because there's only a single path of current flow, so you'll flow through one resistor, second resistor, and therefore the sum of resistance is equal to 3. So you must remember this for TV circuit. The next one we compare is the parallel circuit. Okay, for parallel circuit, you must know that the current split. In this case, current comes out here, I comes out here, and then you split into 2 parts, here and here. So the current is split into 2 parts. If the resistance are not the same, the resistor has different resistance, the current will be different. So in this case, looks like, for example, this one could be 2 ohm. This is 1 ohm. Now, why I guess 2 ohm, 1 ohm? Because the potential between the blue and the yellow must be the same potential across both resistors. So down here, if it's 1 ampere times 2, 1 times 2 is equal to 2 volts. Here is 2 times 1, 2 times 1 is also 2 volts. So they must be same, both are 2 volts. A higher current will mean a low resistance in the parallel circuit. Okay? And then here, the yellow color here, you merge back, and this current here is the same as current here. Yeah, so the current here will be 3 volt, 3 ampere, 3 ampere. So current is the sum of currents, and the voltage is equal. So just imagine this to be like this. Okay, remember this. All the voltage here, all the potential here is all high potential, and the other side is all low potential. You see that across the wire. Yeah. So you realize that down here, if it's, let's say, 3 volt and 0 volt, obviously across all these will be 3 volt, all same, because the same potential across. So the potential of parallel circuit are all the same. Okay? Can I say this part? You must memorize one. The resistance is 1 over the total or effective resistance equal to 1 over R1 plus 1 over R2. All these are in parallel. And the effective resistance is always smaller than the smallest resistance. For example, in this case, I got 2 and 3. My effective resistance here, okay, I put RE lah, effective resistance or the overall resistance, found to be 1.2. Isn't it lower than the smaller one? The smaller is 2. And obviously, whatever you get, the effective resistance must be smaller than the smallest. Okay? So if I have 10 resistors all add together, from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, from the lowest 1 to the highest 10, the effective resistance must be less than 1 because the smallest is 1. Are you with me? Yeah. So you always put 1 over whatever resistance you have, add together first, then flip over, that will be the effective overall resistance. The word overall resistance is also effective resistance. That means the resistance for the entire circuit. Okay, so these are the formulas that you need to remember. Is it okay? All right, so V equal RI, now formula you need to remember, voltage equal current time resistance. Yeah, and then another one is resistance, resistivity. I think it's nothing in there. Oh, could be the other side, resistivity. Okay, never mind. Let's move on. So once it's done already, let's move on to the next one. Practical electricity. So for practical electricity down here, we talk about energy. So we have 2 more formula or 3 more formula to learn. So basically the formula you need to know today is, just now it's V equal RI. Now we have P equal to VI, as well as energy equal to power times time, or VIT. All right, we're going to go through more of this. So you must understand is that electricity is converted. This chapter 15, practical means what is the use of electricity. Electricity can be used to do heating, can use for lighting and so on, or produce sound. So these are actually what electricity can use to produce. Okay, like light bulb, like television, like a handphone, they all produce light. Motion could be a fan, could be even aircon is also motion because they need a blower to blow out the air. All right, washing machine, yeah. And of course, heating effect will be things like oven, electric iron, and so on. So heating effect. So all these are the effects of electricity. How electrical energy is converted to different form of energy. All right, so heating element, you need to know. Okay, you need to know. Yes, you need to know. Good to know this thing. Heating elements are made from things like nichrome. And nichrome has a high resistance as well as high melting point. You cannot have a heating element low melting point, right? Because low melting point means you heat it up, then it melt. You don't want the iron to melt, right? You want it to be hot, but you don't want to melt. So you need to know that nichrome is an example that you study, nichrome in the heating element of electric iron. It has high resistance, so it can produce a lot of heat easily. But it's high melting point, so it will not melt down. On the other hand, you also must know conducting wires are made of copper. Copper is very resistant and heat up very slowly, or should I say it hardly heat up much. So conducting wires are made of copper, very low resistance, and therefore heat up slowly. Any question?
No.
So only remember 2 names, nichrome and copper. How about things like aluminum, silver? They're all actually very good conductor also, low resistance also. Okay, but copper is the cheapest one compared to silver. Compared to aluminum, it's the cheapest form of metal. All right, so the heating, okay, the rate of electrical heating is power. Power is the rate of energy transfer. So power equal to power equal to VI. Okay, voltage times current equal VI. And you need to know this V equal to IR. Remember this one we learned before in last chapter, V equal to IR or I. And if I power equal to VI, then I can say that I can substitute this one inside, right? I can substitute the V inside here. Okay, substitute 1 into 2. 1 into 2. You have P equal to IR times I equal to I squared R. Okay, why do I need this one? You tell me. Why do I need this formula? Now I got 2 power. One is VI, one is I squared R. Why do I need to have 2? I got 1 P equal to VI, but I got P equal to VI squared R. Why do I need this one? Because there are 3 unknowns here. To find power, I need to have both this one, but I don't have R. So in other words, when there's no R, you use this one, no R. This one is you use it when it's no V. You see that? P equal to I squared R. You use this formula to find power when there's no V. Use this to find power when there's no R. Are you with me?
Mm.
Okay, how about next one? No I. So what happens is this, you know that I equal to V over R. This is for number 1. I rearrange, I put I equal to V over R. Okay, this is equation 3. So I sub 3 into 2. So P equal to V bracket V over R equal to V squared over R. All right, so this one, you use this formula when there's no I. Okay, so you realize I can use any of the formula. When there's no R, I use this formula. When there's no V, I use this formula. When there's no I use this formula. So that's why you got 3 formulas. You see that?
Mm.
Okay, right. So that's how you find the power. On the other hand, you can also use the power times time to find energy. Okay, power times energy. So I can say that I use another color. Energy equal to power times time. Isn't it equal to, you substitute this one, sub 2 inside there. Energy equal to power, which is VI times T, equal to vitamin VIT. Take note of the capital V, capital I, because there's a symbol for voltage and current, and T is there's a symbol for time, small t. Is okay? So energy can be VIT, and therefore energy can be any form of these 3, any of this. Can be I squared RT or V squared T over R. Are you with me?
Mm.
So therefore energy can also be okay, I use another color, or it can become I squared RT or V squared over RT. Yeah. Okay, tell me how I derive this formula. How can my E equal to this?
Mm.
How do I get this formula out?
I don't know.
Here. All these are here. Okay, look at this. I highlight for you. Okay, this one is first
But the
formula.
first one is no V.
See that? It can be here. Or I use a green color to show you. Wait, green color. This one is I square R. So it's I square R. You see that? And blue color is let's say V square R. V square R. Do you realize it's all about power times time? But power can be VI, can be I square R, or V square R, either of these 3. All they are power. So if I say, if I don't have an I will use V squared over R times T. If I don't have a V, I use I squared R over times T.
Mm.
Is okay?
Mm.
All right. Another way, this is to find the energy. I can calculate energy, how many joule or energy. But when you want to sell electrical energy, okay, you don't sell by joule, you sell by kilowatt hour. What does it mean? It simply means that any equipment of 1 kilowatt, okay, 1 kilowatt here, 1 kilowatt, I write here, 1 kilowatt. If you multiply by 1 hour, this is the energy, 1 kilowatt hour. Take note, small k, small h, capital W. 1 kilowatt hour is energy. This is energy, okay?
Mm.
But I can convert to joule. Look carefully what I'm doing. 1 kilowatt is 1,000 watt. Times time, 3600 second. Because the SI unit is watt and second in this case, equal to 3600,000 joule. And this is also energy. In other words, therefore, I know 1 kilowatt hour is as good as 3600,123 joule, or 3.6 megajoule. Okay, so that's what the equivalent is. So 1 kilowatt hour, if I convert to joule, I must change the, power must be what? Time must be second. That's why I have power times time give you the joule. Are you there? Please follow closely.
Mm.
Okay, I pause here for a while. Do you want to write down anything? Yeah. Record. Okay, so I have a kettle of 2000 watts. This is electric kettle. Using 240 volt. I use this for 30 days, every day 20 minutes. So how many kilowatt hour of energy is that? How many kilowatt hour energy is that? So you look for kilowatt, you look for hour, you multiply together. That's my answer. How many kilowatt is this?
2000.
No, kilowatt.
Oh, 1.
No, it's 2 kilowatt. 2000 is 2 kilowatt.
Oh,
2000 watt, 2 kilowatt. Okay. How much time is 30 day time 20 minutes in hours?
20 over 60.
20 over 60 multiply by
30.
30 days. Okay, so answer is 10 hour. You see that?
Mm.
Okay, 10 hours. So how much electrical energy? So energy use is equal to 2 kilowatt hour multiplied by 10 hour. 2 kilowatt times 10 hour equal to 20 kilowatt hour. That's how we calculate the energy usage. And because every 1 kilowatt hour is 10 cents, so therefore 20 kilowatt hour equal to 20 times 0.1 equal to $2. Okay, that's all. You get the idea?
Mm.
I always leave my money in dollar lah. Don't try not to leave it a cent. Even though I give me 10 cents, I put $0.1, I know it's $2. Okay?
Mm.
Okay, let's try this one. You have to do this one yourself. I'm not going to help you to do this thing. Can you do this one? This question.
$12.5.
Okay, so how do you do it? Tell me.
The 5,000 changed to 5 kilowatts. Then
Okay,
after that,
very good.
times 10.
Mm-hmm.
Then get 50 times 25.
Okay. And the answer is how much? You say now?
I forgot what I said.
Did you write the answer down?
No.
$12.50, do you get it?
Yeah, 12.50.
Yeah, that's quite a lot actually. Yeah. Okay, can. Okay, the next part is quite theory wise. I'll just tell you what the key things you need to remember. Okay, so dangers from using electricity come from damaged insulation, overheating, and dam condition. I'm sure you know that insulation is damaged or overheating or dam condition. You can get electric shock. Shock 1 and 3 can die of electric shock. Overheating usually ends up in a fire. Just like when people charge, you know, you've always seen a fire in Singapore where they charge the electric bike or the PMD, right? All the electrical devices or even handphone, people also charge under the what you call it, house catch fire because of overheating. All right. So okay, you also need to know how does the main plug wiring works, how does the home circuit works. You need to know the three wire, okay, the three different wire, live, neutral, earth. All right. And then you need to know the safety features that includes fuse, actually not fuse, okay, and circuit breaker, how they work. All right. And okay, explain the reason, okay, why these are fitted onto the live wire. Why all the safety devices are fitted only to live wire? You must understand why. And then you also need to know two more safety feature, earthing of the electric metal casing and double insulation. These are the safety feature you need to have in appliances. Okay. So what happens is this, when you have a short circuit, like in this case, current flow like that, you realize it goes all the way to the other side. So this is a short circuit. Short circuit occurs when current is allowed by accident. Okay, nobody want to short circuit that thing. You spoil the what do you call it, the appliances even through an alternative path with a much lower resistance. So usually something faulty with the equipment, then they will short circuit. So in this case, because this is very low resistance, current will not flow through the bulb in this case. Okay. Now what's electric shock? Electric shock is experienced when current is allowed by accident to flow through a human body. So when current flow through your body, it's called electric shock. Okay, when a large current flow through a body, it can cause electric burn. For example, when a person hit by lightning, you can see that the skin is actually burnt. There's some kind of pattern on the skin, on the burnt scar on the skin. And of course, large current can shock the heart and even cause heart failure and death. Because current can immobilize a person because the electric current flow through the body will lose control. Okay, electric shock. So even a small current like maybe 5 ampere, if you have a wet hand and the 5 ampere pass through your body, you can get electric shock, you can die. All right. All right. But if hand is dry, usually the current is too low, it cannot flow through. I mean the potential is low, it will not flow through. Okay, so current, see the lightning has a current of 30,000. No need to memorize that, but just need to appreciate that lightning is so much higher than the current in the house. The highest you can get in the house is 30. But the lightning, one strike is 30,000. It's 1,000 times greater. That's why people struck by lightning usually die. Okay. All right. So let's look at the three different danger here. I go through quickly. Damage insulation, for example, down here, it could be bitten by rats or animal or dogs even. Okay. Or due to wear and tear, you twist and turn, the wire actually broke. All right. So it's exposed, and the person touches it may get electric shock. So remember, do not touch the damaged wire and disconnect them, and then of course replace the damaged wire. Next one, overheating. Overheating means when there's too large a current flowing through, temperature increases rapidly and then melt the insulation and then cause fire, electric fire. It can cause electric fire. Okay. Or even if you melt the thing, it doesn't cause electric fire, the exposed wire can cause electric shock. When it's a damp or wet condition, water has a low resistance path. It can cause a short circuit. So if you touch the water, the current can flow through you easily. So you can get also electric shock. Like I say, damp environment and damaged insulation is electric shock. This one is electric fire. Of course, this one, when the wire is burnt, it also can cause shock, but most likely start with fire. So down here, try not to have all these plugs or even like hair dryer that works on high current inside the toilet. Okay, it's quite dangerous actually. Okay. Yeah, so generally just make sure that you don't get water come in contact all your sockets. You can just get electric shock. Current can flow out because water is a good conductor. Okay, next one. Let's look at color here. I want to look at here. This is blue neutral wire. Okay, and then there is a brown. Can I see a brown color? Let me see. Brown. Okay. No, this is not brown. Okay, brown. Okay. I just want a brown color. Brown. Okay, brown is a live wire. Oh, this is so dark. Sorry, I didn't expect it. It's just okay. Okay, live wire is brown. Okay, and then the green one is actually the earth. Green and yellow is earth. So I use a green color. Yellow is earth. You see that? Blue is neutral. Blue is actually the neutral. Now, how do I remember? You look at Earth from sky. Look at from the satellite. I mean, look down to the Earth. The Earth looks like green and yellow, right? The soil is yellow. The green is the trees. Green and yellow is Earth. All right. Neutral. Look at the ocean. The water. Water is neutral. It's blue in color. And I remember live wire is brown. You know, when the person touch live wire, you get electrocuted, like then you get burned, you become brown, become char already, become brown. Okay. Or I always tell people, if you touch a live wire, life will be like shit, so it turns brown. Your body will turn brown, you get burnt. So remember, don't touch the live wire. Touch already, life will be like shit because you lose your life. Therefore, I remember it's brown in color. Yeah. It's okay? Okay, so remember the three color and remember the position. You need to know in the power socket. In the power socket like that, in the wall socket, there are 3 holes. All right, and then there's a switch. There are 3 holes. So what does the hole represent? The position of the first hole represent earth here. So the earth wire from the equipment goes to this pin and you plug inside here. And then neutral is here, N is here, and live is here. Okay, live is this pin. This is live pin. Okay, and this is neutral. Are you with me? So why you see that the live has a special pin here? The pin is below, you know. It goes to the current that comes out from the socket live will pass through the pin up to here and then go through the fuse and then connected to the equipment, go to the equipment. Okay. So the fuse is always on the live wire because I want to cut off the voltage. The voltage is changing on the live wire, not in any other wire. The neutral wire is kept at 0. The earth wire is also at 0. All right. It's only the live wire that the voltage will fluctuate. It's okay. So the live wire voltage will fluctuate like that. Go up, come down, go up, come out, go up, and so on. So this is plus 240 volt. Below is minus 240 volt. So the voltage will fluctuate in Singapore. And then you go back to M minus 240 volt. Are you with me? So the fluctuating live allows the current to flow in and out of the equipment. Now the neutral is always blue. Neutral is never changed. It's always no, blue is always 0 volt. It just stay at 0. You don't have to worry about what it is. Just stay at 0. And then of course this earth wire is actually connected to the ground with 0 volt also. Okay. Okay, this is a fuse. I know it doesn't look very nice like a fuse. The fuse looks like this. There's a metal cap here. There's a metal cap here. Center, whether transparent or not, it depends. It can be a opaque or transparent. But in the center, there is a wire. Okay, there's wire here. What does it mean? It means that the current touches this metallic part will be conducted through the wire to the other side of the metallic part. So these are drawn like that. Are you with me? The fuse has a wire where when the current goes through is too high, higher than the rating of the fuse, the wire will melt and then you'll cut off the circuit. You'll form a open circuit. Okay? Okay, let me just highlight to you this thing. A fuse is a safety device with a thin wire that disconnects a circuit when excessive current flow through it. The thin wire melts and disconnects the circuit. And when this when excessive, okay, I'll show you here. When excessive current flows, the metal wire in a fuse melts and then disconnect the circuit. And we say that the fuse has blow the fuse. Okay. So the current rating is what's the current rating of the fuse? Is a minimum current that will melt the wire. All right. So in other words, in my operating current, it must be higher than operating current. Okay, wait, let me write for you. Fuse rating must be greater than operating current. So if my equipment is a 3 volt, no. Equipment is 3 ampere, work on 3 ampere current, then my fuse rating is likely to be 5 ampere, slightly higher than the 3 ampere. So the fuse rating must be slightly higher than the operating current, cannot be equal, cannot be lower, all right? So you see a 5 ampere fuse means the current flowing through inside is up to maybe 4 point something, but never reach 5. Reach 5 means it's gone already, it melt already, okay? Okay, next one. So fuse is one. Second feature is circuit breaker. I use different color to highlight for you. A circuit breaker is an automatic switch that disconnects a circuit when excessive current flow through it. And once activated, it's called trip. Like for example, your house blackout and your parent tell you, oh, the circuit must have trip. Circuit breaker trip already. So it disconnect. Okay. Remember in 2020 when we had the COVID just started, Singapore called the event then called circuit breaker.
Mm-hmm.
Do you remember circuit breaker?
Yeah.
Yeah, what's the purpose of circuit breaker? Circuit breaker is to disconnect, to break the spreading of the COVID that time. That's why I call it circuit breaker. So by having a lockdown, right? I think they call it a lockdown, right? During circuit breaker, what happens is that if everyone stay at home, then the virus cannot spread. It's like you disconnect the people socially so that the virus cannot spread. You know what I mean? So circuit breaker is a disconnect. So circuit breaker works very simply. Where's the switch? Okay, I tell you what, I'll show you a real circuit. Have I shown you circuit breaker? I'll show you a real circuit breaker. Give me a second. Okay. Okay. So funny. Yeah. Circuit breaker. I just pull circuit breaker. They show me the real circuit breaker. Okay. All right. Not circuit breaker. This one. This is circuit breaker. Switchboard. See that? Okay, I'll show you how it looks like. Okay, this is circuit breaker. Okay. So if you trip, it goes down. If you push it up, that means it's the whole thing, all that are connected. So each switch represent a different circuit. You can see down here, they just show you something, the circuit. So every switch is for certain different circuit, like for example, lighting circuit, the socket circuit, and so on. Are you with me? Yeah. So I think I'm sure your circuit breaker board is quite big, not so small actually. Bigger than this. I put Singapore. Electrical box, this box. Yeah.
Isn't it called DB box?
What box it called?
The DB box, isn't it?
TV box?
DB.
D.
DB box. Isn't it not called that?
I don't know what you call that.
Yeah, you can search at DB box.
How to spell?
D and B.
DB box.
Yeah.
Okay, interesting.
Yeah. Is that right?
Oh. Wait, it's not.
No?
Oh yeah, it can be. It's a distribution board actually, box, correct. Yeah. So DB box, okay, interesting. Okay. Actually in the, yeah, how do you know this term?
I thought everyone uses this term.
Is it?
Yeah, my parents also call it the DB box.
Oh, layman term. This is a layman term, I guess. Electrical distribution board. Yeah, maybe it's another term. Okay, in the textbook, you call it the miniature circuit breaker because we want to emphasize the purpose of the thing is to break the circuit. Yeah, correct. Yeah, you're right. So it's the same. See that? So you push up means is everything is on. If you drop down means certain part is switch off, trip already. Yeah. So my home's one will look like more like which one? Let me see. Something like that, but bigger. Yeah. Have you
Can
seen
this
yours
thing
before?
give you electric shock
This one?
if you touch it? Yeah.
No, unlikely because it's all plastic. There's no direct contact to the inner part. All the switch are all plastic.
Mm.
But we still scared the current jump out. We usually use a wood broomstick to push it out. Yeah, really. Because current flow through here is quite deadly. Okay, it's very high if it can come out. Yeah. Let me see. None of them looks like the one I have at home. Okay, fine. Okay. Interesting. Breaker box. Okay. Singapore circuit breaker box. HEB circuit breaker box. Okay, we call it circuit breaker. Why they call it DB box? Right? Is that very interesting? Yeah, mine is bigger than this. Have you seen yours before?
Yeah.
I think it's bigger than this, right? More, right? About 10, 20. More than 10. Yeah. Okay, anyway. Okay, so off it aside. So what's so special about this circuit breaker here is actually there are a few kind. The main one that which I used to see is called miniature circuit breaker. All right. So basically, when current flow through, if it's too high, higher than the current that you're supposed to flow, then you will just detect and then switch off the trip. Okay. Earth leakage circuit breaker. This one is when there is a leakage to earth. Earth leakage. They find a current flowing to earth. Detection of current flowing in the earth circuit. Then you will break it. Or residual current circuit breaker. The difference in the current between the live and the neutral and this neutral. Basically, you know, what flows through the live will go to neutral, right? Whatever flow for neutral will go to the live. So actually, it's like alternating current. Unfortunately, if the current in the live and the neutral are different, what does it mean? Something must have gone somewhere. I mean, it could have gone to the earth. So for example, live come in, the current is 13 ampere, but what goes out through the neutral is only 10 ampere. So 3 ampere must have leaked somewhere to the earth or whatever. Maybe through the person's body, you know, the 3 ampere flow through the person's body to the earth. So that's why there's a difference. They call it residual current circuit breaker, right? Yeah. So anyway, the whole idea is the fuse will break the circuit by melting the wire. Look carefully, the metal wire in the fuse melt. If the fuse is able to when the fuse function to disconnect, is permanently melted, so it cannot reset at all. So the fuse is a device that it keep on changing one. If it spoil, you gotta buy a new one to replace. You cannot. There's no way to repair. It's okay. Hello, can you get it? You must buy the same rating. If the current inside this equipment is, let's say 4 ampere, they call the operating current, then my fuse could be 5 ampere. If my operating current is 6 ampere or 5 ampere, then my fuse rating could be 7 ampere. Usually is the odd number here, I realize. 10 is an even number. So it can be just 1 or 2 ampere higher than the operating current. But you must use back the same fuse. If not, then next time they cannot function properly. Okay? Why do you want to cut off at 5 ampere? Because above 5 ampere, my equipment may spoil. Before it's permanently spoiled, the sudden increase in current, you want to cut a whole circuit off. Okay? Now, so circuit breaker can be switched on and off. You switch off, you just disconnect. Disconnect all the spoiled equipment and then you push it up on again. Then it's working. But the fuse must be changed. All right, let's move on here. This is the earthing of the metal casing. So what happens is the metal casing has one more earth wire coming out. This metal casing. This wire coming out is the earth wire to the socket. And the socket will connect to the ground. So this is the socket connected to the ground. This earth wire come out from the pin. Come out from here. Okay, this one. Earth wire. Alright? And then can go in the earth, in the ground. So it's always connected to earth. All right, so we have a live wire and the neutral wire, and then the casing has the earth wire. The earth wire is not connected to the motor, it's connected to the casing. Okay, so when a person touches the metal casing of faulty equipment, the person avoids electric shock because current tend to flow to the earth than to flow through the person. I show you. So metal casings are connected to the ground through the earth. So when a person touches faulty appliances on the metal casing, the person avoids electric shock. Why? Because very little current flows through the casing to the person. Most of the currents are flow through the earth wire already. Okay? Because it's connected here. Now, how does it even happen? Look carefully what I'm doing. Look. If my live wire is broke and touch the casing. In other words, my live wire did not connect to my resistor or my motor. The thing is disconnected and touching my casing. So casing become live. Are you with me?
Mm.
Yeah. All right. It could be the other side, it could be like that also can. You see that? For my motor equipment, I connect to my casing accidentally. Instead of going back to neutral wire, I go to the casing. So casing is still live. Okay. All right. Another idea is double insulation. So double insulation is a product design having 2 layers of insulation around the live wires in the appliances. So usually 1 layer is inner layer where you seal off from external. Okay, so the live wire connect to the motor or connect to the whatever thing, and then yeah, insulated. And then the second insulation is outside the casing. Okay, for example, if you have a printer, let's say a printer, printer to print your paper, it's made of plastic. So the second, you see, first layer actually prevent current in the wire from leaking to the internal component of the appliances. And the second layer actually prevent the leak current from leaking further to external casing. So the whole casing external is plastic in this case. It's okay? Usually it's plastic. If outside is metal, outside is metal means within the metal there's a layer of plastic. We do not see only the design. You know what I mean? Yeah. So down here is of course using the earthing, okay, to direct the current away so that user will not get shocked, or use double insulation so that the current can't leak out. Yeah. Okay, this is the earth circuit. There's a main circuit breaker. In short, they call it MCB. MCB. MCB is a main circuit breaker, or you also use the word miniature, means small size circuit breaker. So live wire come in. You see the live wire come in here. It passed through the circuit breaker. It passed through the fuse. You see there's a fuse here. All right. It passed through the switch. The switch must be on the live. Okay, the switch must be on the live. And of course, there are other switches here. You realize that? Okay. And then this is the main circuit. The circuit that you plug your socket. When you look at the wall socket, all these are the main one. Why is it the parallel circuit? Because every socket is independent of the other. So if you plug in the first socket, second socket, third socket, it doesn't matter. As long as you plug in the socket, you're on the parallel circuit. You draw your own current, you're not going to affect the other components. Is okay? Okay, so let's move on. Yeah, so we learned basically two formula down here. One is talking about the power, and power times time is energy. But energy usually calculated in kilowatt hour and then multiplied by the cost. All right, so that's what is important here. You need to know about shock, short circuit electric shock. You need to know about damage insulation. You need to know about overloading, heating, wet environment. You need to understand the main plug. Our main plugs have 3 different connections. The center on top is earth. This is neutral. This is live. Okay. It looks like what? NEL, northeast line. Yeah, just remember on top is earth lah. And then the right is live. Yeah. Okay, I think right-hander. If are you right-hander? You are, right?
Yeah.
Right-hander is easy to remember. Or live is here. Okay, you know. Most important here is life. Okay, so anyway, that's all for this thing. Safety feature is fuse and circuit breaker. And of course, other features in the product includes the earthing, the metal, and of course, the casing as well as double insulation. All this is to protect users. So actually, there are many, many layers of protection so that when we use equipment so often, we don't get electric shock. Even if you get electric shock, the circuit breaker will cut off the current so that you will not get, killed by the current. In fact, a lot of people will got small electric shock experience. All right, like for example, my laptop, because you use a lot of time, your hand touches the body of the laptop, right? And then maybe some part wear and tear. It's supposed to be plastic coating outside, but it's exposed, so you can get a little bit electric shock when you touch the thing. Yeah, but be careful now. Such thing means that the laptop must be quite old already. Yeah. Okay, let's look at this thing here. Let's go through an example here. You see, I want you to know that there's a fuse and there is a switch. There should be a switch down here, like that. Okay, what am I doing? Sorry. There may like that. There's a switch. Switch. Wait, let me think. Switch. Yeah. Switch and fuse is on live, correct? Switch is before. So I can change the fuse actually. But doesn't matter lah, as long as on this line. Neutral side don't have the switch or the fuse. And then the earthing is on the casing. So electrical fault in the oven cause current to flow through the casing. Explain why the fuse blow. Why is it that when current flows like that, look carefully, when current flows like this, in, okay, and then flow to the casing, out, like that. Okay, flow through the casing. Why is the fuse blown? Okay, the whole idea is, during electric fault, the current flow through the earth wire to the ground. Because the resistor earth wire is small, the current become very large, and therefore exceeded the fuse rating and caused the fuse to blow. Okay, I will say that causing the metal wire in the fuse to blow, to melt. Metal wire in fuse to melt. That's why it blow. Because my school, I think they want to do this thing, melting a fuse. It's okay? Yeah. Because if we don't say the metal wire in the fuse to melt, then people wonder how do you blow the fuse? What do you mean the word blow? The blow simply means melt. Okay? So describe how the location of fuse prevent user from getting electric shock. The location is located here. So what happened is that when the fuse blows, the electric supply is cut off and the current no longer flows from the live to the oven. Okay, so the fuse will cut off, so it cannot flow to the oven anymore. So even when the person touches the oven, the current does not flow. Are you with me? It's really cut off already. All right. Okay, let's try this. Can you tell me the answer for this? Okay, what's the answer for this?
C.
Okay. So down here, let's see. You're saying that you said answer is C, is it? Okay, so what happened is this. Where will a person get shocked? When the current leakage, right? So when the person gets shocked, will the current go very high?
No.
It will not, right? Then the fuse cannot melt. Okay, A fuse is let me see. Let me go through a fuse again. I feel very interesting here. Okay. When excessive current flows through a fuse, when will excessive current flow through a fuse? Excessive current flow through a fuse when there is a short circuit here. See that? A short circuit where there's a low resistance path, so the high current flow through, and high current flow through cause temperature to rise rapidly. Okay, that's all. Temperature go very high. So it's more for preventing the wire for overheating than to prevent electric shock, because you don't need a high current to shock a person. You just need a 5 ampere. Remember I told you, a 5 ampere can give a person a nasty shock. You will not die immediately, but you'll lose control of your body, and then sometimes the person may get heart attack. Sometimes the person just get the electric burn. Okay, so a shock. So the fuse basically is to cut off high current, higher than operating current, which is obviously over 13 ampere. Is prevent the overheating of wire. Answer is A. Okay, and it's fitted in live wire because if the high current flows through, then certain part of wire may get heat up and then may cause electric fire. Okay, yeah. So overheating, more overheating than electric shock. Okay, let's go at this one. Can you try this question? 1 and 2.
Wait,
Do you have a calculator?
yeah, wait, I think.
Okay, have you found?
$1.75.
Okay. What's the kilowatt first? Let me see. 5 divided by 60 times 6 plus 1.5 times 8 times 14 cents. What's the answer?
$1.75 B.
Very good. Yes, correct. Very good. Okay. Which one is not a safety feature of a 3-pin plug? Huh, I'm sure you know this one. Which one is not part of a 3-pin plug?
Connection to Earth.
Huh? I thought 3-pin plug inside connect one of the pin connect to Earth. You mean your 3-pin plug has a built-in circuit breaker inside?
Oh,
No, right? You only have a fuse only, right? Answer is B. Answer is B. Okay. Okay, next one you need to. Oh, this is a structure question. You need to calculate a bit. The heating rate means finding the power of the heater. All right. Okay, so what's power rating?
Wait,
Three
what
formula.
does the I stand for? The P
Current.
equals,
Power equal to voltage from current, or
yeah,
power equal to I squared
Ohm,
R, or
4,000.
power equal to V squared over R. What's the answer?
4,000.
Right. Oh, here is it. Let me see.
Is it not 10
Time.
times 400?
I know, but are you sure this is I? This is R.
Ah,
Is there any I here?
no.
So which formula can I use?
The third one.
Okay, very good. So answer is P equal to V squared over R equal to 10 squared over 400, right?
Mm-hmm.
Equal to 1/4 lah. Okay, next one. Connected between A and B here. 2 ohm. Calculate the current flowing through this 2 ohm. These are parallel, so you can calculate separately. Just calculate here separately.
What's the formula?
Sorry?
What's the formula?
Okay, what you gonna find?
The
I,
current.
right? What are you given? You're given V and R. So I equal to VOR. That's all.
Oh,
Equal to 10 volts over R is 2 ohm. Equal to 5 ampere. Yes, 5 ampere. Okay? Okay, next one. The heating rate of the 2 ohm wire. Basically find the power in the 2 ohm wire. P equal to what?
VI.
Okay, can. VI. What's my V?
10.
And what's my I?
5.
5. Answer is
50.
50 watts. Okay. Suggest how connecting the 2 ohm wire affects the battery. How does connecting one more wire affect the battery? Because originally I have current flowing through here, right? This one, originally. Then you connect one more wire, I have one more extra current. Okay? By right, the current here and the current here are independent one. Whether I connect the 2 wire or not, this wire current flowing through is the same one. No change for this. So tell me, what is the effect of this one? How connecting this 2 ohm wire affects the battery? Okay, look at the difference in resistance now. Is it much lower?
Yeah.
So much lower means a very high current will flow through here, right?
Mm-hmm.
So what happened to my battery?
It become hot.
Yes, high current flow, you make it hot, as well as it drain very fast. Is it okay?
Mm.
So the 2 ohm wire has a very
Drain
low
very
resistance.
Oh.
So a very low resistance, so very high current means the battery will drain off. The current will coming out is very high, it will drain off very easily.
Then the other one is because it heat up.
Huh?
Then water one is because it heat up.
Yes, correct. Heat up the wire, it may cause electric fire. Yeah, I'm doing it right. You can understand, right?
Mm.
Yeah. Okay. Overheating produce electric fire. All right. Let's look at something like that. What's this? Let me see. This is a rice cooker. Yes, rice cooker. Can't even see clearly. Never mind. Rice cooker.
Current is the I.
Mm-hmm. It looks a bit like this.
Mm. 900 divided by 240.
Show you the diagram. Looks like this. Okay. Wait, 900 divided by 240. And answer is?
3.75.
So you use I equal to what?
V over P over V.
Yeah, okay. 900 over 240, right? 3.75 ampere, right? Okay, can. Next one. Which fuse do you use? Your operating current is 3.75. Who is closest and yet still higher one?
5.
Yeah, I use a 5 ampere fuse, okay? Why? Because the fuse rating must be higher than the operating current, but
What happens
not
if
too
it's lower?
high. Huh?
What happens
What?
if it's lower?
Straight away you melt already, oh? Because operating current is 3.75. If I use a 3, what happened? The 3.75 exceed the rating, then you'll melt, no?
Then what happens if it is too high?
Use too high means that when the current goes up, you still cannot cut off. It continue to flow at high current. Then the heating will happen. For example, I only use 3.75, but I use a 15 amp rating. I use a 15 ampere rating. Obviously, you cannot reach 15 easily, right?
Mm-hmm.
So there could be maybe current leaf go up to 8 ampere, 9 ampere, 10 ampere, and then hot enough to melt the thing, but yet you're not cutting off because the rating of the fuse is a bit too high. So it should be slightly higher so we can protect the equipment also. In other words, as long as you want to exit this and you want to stop. If it's too high up, like for example, you use 20 ampere fuse, the thing need to raise by 6 times then before it cut off. By then your equipment spoil, the wire burn already. Too hot, too high already. You know what I mean?
Mm.
So why okay the question is here lah. Why 10 amp fuse is not suitable? Answer is the 10 amp fuse is too much higher than the operating current. It's 3 times the operating current. Okay?
Mm.
So if it's too high, what happens is that even though the current may be raised, okay, higher than the normal operating current, hot enough to melt the wire, and yet you haven't reached the fuse rating, so you will not cut off the current. So it should be just slightly higher, about maybe 2 ampere higher. Okay? Can?
Mm.
All right, let's look at this circuit here. This is another circuit. You want to try this?
I don't know.
Look at the pin. These are the wire that comes out from the
3
equipment.
pin.
Yes, of course, 3 pin. Because there's an earth wire coming out, it must be 3 pin. There's a wire that connects to casing, right? You need the 3 pin. Okay? Can?
Mm.
So the third pin on top is for connection to the earth wire, which comes out from the casing. So both earth and neutral are at 0. Explain why the metal casing is connected to earth instead of neutral. Why does casing not connect to the neutral?
Mm. I don't know.
Hmm?
I don't know.
Okay, if the earth casing is connected to neutral, the current flow in from the live to the neutral to the earth casing to the casing. Then my casing become live. Right now. Let me see. Current will flow. Okay. Okay, let's look at this. Imagine this. Connect to here. Casing only. And then the earth wire, live wire touch the casing. What happened? Imagine my neutral wire connect to casing. And this one also touch casing. Look at my current flow. I use
It will
a
be
thicker
on the
one.
metal case.
Yes, the current flow like that, like that, like that, like that, like that, like that, like that. So tell me what happened to the casing.
It will be damn hot.
It will live, right? Become live, right?
Uh-huh.
And then when you touch, what happened?
Electric shock.
Yeah, you get electric shock actually. Possible electric shock, right? Yeah.
Mm.
Let me see. Correct. Possible electric shock. And you know the circuit breaker, there's one that when the current flow in the earth, the circuit breaker will trip the thing. So if it doesn't connect to earth, then there's no current flowing here. It just flows through neutral. And then they may not even know the current has leaked. See that?
Mm.
Yeah, equipment spoil, but current is still flowing through the live to the neutral. Yeah. So we do not know that the current actually leaking already. Until we touch it, of course we get a shock lah. Okay. All right. Oh yeah, we're done. We're done. Okay, so right. I think you can try the MCQ yourself. I mean the MCQ book. Yeah.
Oh.
Right. What time do we start?
It.
Oh. Oh, okay. Still got time. Let me stop.